Okay. In this presentation, what you're going to see is a unique workflow that's developed for unconventional resource space using a couple of technologies within Decision Space Suite, which is going to help our customers to minimize the cost and also to drill more productive wells in a safer environment. So before I jump into the demonstration, let me give you an overview of it. So what we're going to do is, first and foremost, we'll understand the challenges we have from a field of choice in relation to, let's say, the pad placement. And once you understand the challenges on the surface side, the next thing we're going to do is look at our field and any subsurface information we might have from geology standpoint. So what I'm looking at here is historical well data and the log information. From that, I can figure out what is my top and base of the reservoir of interest. So you know what's your reservoir of interest in this particular field. Once you understand, you can actually build a framework right around that area to come up with how much of the rock is actually available, the resource rock available for this particular field. Next thing what I'll do is I'll incorporate different phases for the formations and also porosity and permeability, which is more like reservoir properties, to understand and build an earth model. So what I just did is I'm going to go through the entire reservoir model and I'm going to understand how much of this reservoir model is occupied by organic content. And that will give me an idea how I can effectively lay these wells and drill them so that I can efficiently drain the reservoir. So that's going to affect our bottom line here. Next thing what I'll do is I'll run through different exercises of well planning, field planning for the entire field. And from those field plans, I'll come up with an optimum field plan that actually will work with our particular scenario. So till now, what I did is I built an asset model for our resource play. Now, as you know, a model needs to be calibrated in order to get it to the real situation. For that, I'll bring in a live well, and then I'll incorporate that as part of the system. So that's what I'll be doing in geosteering, where I'll actually show how I can keep that well in the sweet spot along the way as it is drilled. And the greatest benefit that we have with the tools that we can incorporate here is the framework or the surfaces that we build. So as you're correlating these logs, you can update the frameworks on the fly. That's what we call the dynamic frameworks to fill. And once you assure that you laid the lateral in the right part of the rock, the next one is the most expensive and productive part of our field development, which is basically the stimulation. This is where you'll make sure most of your microseismic events are actually stimulating the right part of the rock, and of course it's going to affect our production eventually. And this is a loop that I'll be combining together. So it'll be an updating model. As you get more and more information from the logs, you'll update your reservoir model. As you get more and more information from the well planning, from stimulation, you'll be updating your field plans. So you'll be re-refining those field plans. So that's what we'll be seeing. My name is Rishi, and I'm the technical sales manager for North America. With me, I have Duane Pratt, who's actually driving this software. So what you're looking at here is different shale plays in the United States. So if you notice, there's a lot of potential in order to make this country energy independent. With gas prices being so low, there's a lot of demand for the oil-rich zones, which are designated in green up here. You see the one on the top is the Bakken, and the one on the bottom as well. So for my presentation, I'm going to focus on one such active resource play very close to us, the Eagle Ford. So let's take a closer look at the drilling activity in this particular area. So what you're looking at here is three different zones. You see the top zone is basically the oil-rich zone, and the bottom zone in red is the gas zone. Right in the middle is that condensate zone. So if you notice it, there's explosion of wells drilled in the oil-rich zone, designated by those dots in green and red. So for our presentation, I picked one such active oil-rich zone, and let's take a closer look at that particular field. Now what I can do with the Decision Space Suite is I can incorporate all the geospatial information directly into the system. That's what you're actually looking at here. I use the ASRI engine capabilities we have within the GIS module. I went online, cropped the area of interest. I took that aerial image and I draped it with my digital elevation model in order to understand my topology or the lay of the land, if you would. And the other thing I did in here is I can incorporate the lease information that I have accessible from county as well, where I can access directly from this particular tool. So what you're looking at here is 3 different leases, the pink, the blue, and the yellow. Those are the 3 leases we have. And if you notice it closely, right between the leases, there's some engineering constraint data. For example, those white lines you're seeing, those are the road lines that are actually following right in our leases. And also, right in the middle of those leases, there's a river that flows. And if you notice it, the northwest corridor is pretty terrain and hilly, and also the environmentally sensitive area in green right there. So we want to make sure we don't position any of our pads on that slope and risk the mechanical stability of the pads. And also we want to stay away from that environmental region so that we minimize the disturbances as much as possible. And not only that, we don't want to place any of our pads in the river either, and also maintain the setback within the leases for our pads as well. So there's a lot of challenges as far as the pad placement is concerned for this particular area. This is how it would be. You won't get perfect squares. It will be irregular. You have to selectively look at the reservoir properties for the organic content and the properties of the rock in order to effectively lay out your laterals and develop these fields. Now, if you go take a closer look on the extreme right lease in yellow, what you're seeing in red are the wells that are actually drilled already in this area. Now, let's take a closer look at the drilling and production data and see if we can learn anything from them for our field planning process. So what you're looking at on the left side of those 2 wells have a very good production compared to the other 2 wells. Now, what is actually driving the production for those left 2 wells? For that, what we can do is we can use tools like the Shale Expert, XBAT, in order to quantify the total organic content within the rock and also mechanical properties. Let's take a look at a couple of those maps. So what you are looking at right now is basically the total organic content. So if you take a look, those 2 wells with high production and also the other 2 wells, most of them, they fall in the same uniform band of green color, which indicates it's not the total organic content that's driving the production on the left 2 wells. Now let's take a look at the rock properties in this area. Now, those 2 wells on the left, they fall right smack on that high brittle area which is designated in the red, and that's what is actually driving the production in this particular field. So this is a good information for me to understand before I go ahead with my field planning process. Now let's see if we can learn anything further in relation to the drilling and production point of view for these wells in this area. Now what you're looking at here is the topology or stratigraphy of the field. So if you notice it, Eagle Ford is that middle zone which is sandwiched between the upper Eagle Ford and the Buda zone. So that's the area of interest for our well planning. So also you want to make sure you don't want to get any close to that Buda zone which is rich in limestone and acid gases. So you don't want to take the sulfuric gas inside our wells and eventually shut down the entire facility. So you want to minimize that. Other thing for Eagle Ford, it dips down stratigraphically from the northwest to southeast corner. So usually most of the time what the operators do is they have an up dip kind of configuration with a heel down and toe up in the reservoir so that they can get effective drainage out of these reservoirs and also during the fracking process. So that's an important information for us in order to plan our well plans as well. And the other thing we noticed is it's not just enough to lay the lateral in the sweet spot. You got to lay it very effectively. What am I talking about? You need to make use of the natural fracks that exist within the rock and line up your well in such a way that they stay perpendicular so that you can drive the propellant into those crevices, keep them open with the sand mixture, and the chemicals will do their action to propagate those fracks down the road. So that's the key important thing, lining up our lateral along that stress directions. Now, other thing we noticed with the operators in this area, they're actually drilling those wells which are designated in the green very close to each other so that there's a nice overlapping between adjacent stimulation treatments which are designated in red ellipses there. So you want to avoid the top 2 scenarios where you're leaving majority of the rock unstimulated. Okay, now let's take a closer look at the frac data on one of these wells. So you're just looking at different stages for that well which is stimulated from the toe to the heel. What I'm going to do here is the direction or the azimuth of those frac data goes along the minimum stress, the frac direction, the natural frac that exists in the system. I'm going to take the orientation of my well in relation to those frac direction and also the average frac length I have for these stages, and I'll incorporate that in my field planning process. Now let's take a closer look and see how we can incorporate that. So we already went through the challenges we have from the surface point of view for a pad placement. Let's take a closer look at our subsurface and see what we are getting into. Now, in blue, what you're looking at is the historical well logs that we have in this particular area. So we got all those wells and logs that are tied with it. And right there, you're looking at a couple of surfaces, the top and base of our lower Eagle Ford. That's the area of interest for us. Now, how did I get to this point? This is a unified system. It's an integrated part of geology, geophysics, earth modeling, reservoir and production. So geologists went into those historical wells that we have in this particular area. They inserted the tops of the top peaks for my well that designates the top of my reservoir, and the bottom peak, the base peak, where it actually hard kicks into limestone. They correlated those peaks for all those wells and gridded them up. So right now what we have is the two surfaces, the top of our lower Eagle Ford and the base of our lower Eagle Ford. Now the next thing what we did is we created a framework, if you would, for this particular zone to understand the total size of our reservoir. And then all we did is we incorporated the facies that you're seeing on those logs and also the properties of the rock in relation to the porosity and permeability in order to come up with an earth model. So the earth model is going to dictate what are the zones of high total organic content, okay? And that's where we need to go closely into the earth model, understand the TOC, understand the mechanical stresses that exist within the rock, and accordingly align our laterals so that it can effectively be drilled within this area and efficiently drain from the reservoir. So now for this particular well planning exercise, I will actually use the top and base surfaces for my field. Now, what I'm going to show you is 3 simple step process. So what you're going to look at is the map view on the left, and then I'm going to actually incorporate the average frac length that actually took, okay, from that one field I had. So I'm going to incorporate that for the spacing of my wells. And then, of course, the length of my lateral, the number of stages I can have dictates that length of the lateral. So I will use that information. And also the information I have in relation to the orientation of my well in relation to the natural frac that exists in the system. And I gave that up dip kind of configuration with heel down and toe up so that it can efficiently drain this reservoir. Now let's go ahead and create the laterals. Now remember, the laterals is the key. That's what dictates the production for this entire field. So what I basically did is I incorporated the best practices from the neighboring wells, and I incorporated that from a field planning. So you're looking at that yellow and orange, that's the heel and toe. It actually uniformly fills all across those leases, okay, and maintains that setback as well. Let's take a closer look in the 3D view, if you would. So again, these are the laterals that stay within the reservoir. So they are not any constraint as far as field planning is concerned. So that's our first step. The second step I'm going to do is basically look at my surface challenges and incorporate the pad configurations I have access to. Right now, I have a couple of pad configurations. So I'm going to ask this tool to go ahead and use those pad configurations and figure out optimally where it needs to lay out a 8-slot pad, where it needs to lay out a 10-slot pad. So let's go ahead and do our pad placement. Okay, so what you're looking at in red is basically the 8 and green is the 10 slot. So remember that corner, for example, it put an 8-slot pad in red because we have less number of laterals. And on the right side, the green slot, we have more distribution of laterals, so it places an 10-slot pad. If you go take a closer look, it avoids that river zone, and then it also avoids that environmentally sensitive area. It even makes sure it doesn't put any of those pads in the terrain, the slopey terrain, so that we risk mechanical stability of those pads. So it took all the challenges we have. Also, you can have the setback that whatever the county wants. Now, the next part is basically completing our horizontal plans. So in here, what you have is different types of typical directional driller would need. So this is all the technology from Sperry's expertise and also from Landmark's compass technology. So we incorporated that. All I did is I brought in a couple of horizontal well plans. In one case, I had 8 as a dogleg. In the other case, I had 10. Again, you can play with all these directional parameters. So all I did here is I gave options to be considered in order to develop this entire field plan. So let's go ahead and develop our field now. That's our third step. So there you go. It went ahead, it used up all our laterals and developed this entire field. Now this is actually our first pass at our field planning. If you notice it, most of those field plans are actually coming from a common slot. It's not actually using our slot arrangement. This is where what we can do is we can go ahead and further optimize our entire field and come up with more robust, drillable wells. So what you're looking at here is the pad association. In here, the very first one is using only 50% of the slots. So there, I can lower it to a lower pad configuration. By that, I'm lowering the total cost for this field. And not only that, this is going to help us to understand how many pads you would need, what kind of pad sizes you would need. This would be a great benefit for our customers so that they can secure those pads in time, especially in Eagle Ford, which is very, very active. This is a key for them, and that's a great benefit for our customers compared to their competitors. The other thing I can do is I can give a range of parameters for my initial and final conditions, like for kickoff and hold angle, so that I can build that curve and keep the lateral in the reservoir, and I can also account for any separation issues for the shallow part of the reservoirs before they kick off into the reservoir zone. So let's go ahead and apply that and see how our plans are going to look like. So there you go. It went ahead. See how the shallow part of our well plans are split using that separation factor. And then it has a nice curve built. And it actually had that up-dip kind of configuration for our reservoir. And it used up pretty much all of our laterals. Now let's take a closer look at our, there you go, you got that up-dip. Let's take a closer look at our surface in relation to our pad placement. So this is a good tool. It can actually help us to understand the rig scheduling as well. For example, you know that red pad you're looking at, you can actually understand where you need to put this pad, where you need to move this pad after you're done with this particular site. So this is a good tool to understand where to go from one place to another place as well. Now, the real power of this tool, we did whatever we just did, that's basically 6 months work without a tool like this. The real power of this tool is it drastically reduces that cycle time to come up with different field planning scenarios. What kind of scenarios am I talking about? Some operators in Eagle Ford, they want small laterals and more pads. Some actually want long laterals, less number of pads. Some want their direction of orientation in relation to that minimum stress direction around 10 to 15 degrees so that they can drive in the fracking mixture in the right crevices. Now you can actually incorporate all those scenarios, whether it's pad sizes, costs, or laterals, whichever it is, from horizontal well planning. So that's what you're actually looking at. That's the real power of this tool. It can actually build multiple scenarios like this. Think about it. You don't have 6 months to just change your orientation a little bit. This is the same exercise one of our customers has gone through up in the north, where he actually reduced, he ran like 30 to 40 different iterations or scenarios, if you would, and he's able to shave off 15 days, almost half a month of drilling time. Not only that, he reduced the number of pads by increasing the length of the laterals, which means he reduced for fewer facilities, less road construction, and other pad services and operations. So he was able to reduce $12 million off the bat just from the planning of it. So that's the true power of this application. Now, what we did so far is basically build an asset model. So let's actually go ahead and take a closer look, see if we can actually drill in that high brittle area and get the similar kind of production like we did, okay, in the first, at the start of my presentation. So you're looking at a well of choice which we picked in that high brittle zone. Let's take a look at that in the 3D view. So what you're looking at is again the top and base of our reservoir, right? And those are the two, what we call the frameworks. What do I mean by that? For example, if you take the pick where it actually first makes that intersection with the reservoir, if that doesn't line up with the log signature, you just click on the pick and update it. It automatically updates the surface all around it, the up dips and down dips. And not only that, all the adjoining surfaces below that, they get updated as well. So that is the flexibility we have. This is why we call it dynamic frameworks. The framework updates on the fly so that it gives you a better picture ahead of the bit where your reservoir is. So if you notice it in the section view, what you're looking at in yellow is our plan, and in pink is basically the 3D survey. This is the information that can be brought in real time because this tool actually incorporates real-time data directly as well. So we successfully built the curve and geosteered it. Halfway through the well, what we noticed it has actually had sudden drops in rate of penetration, and our mud logger has really reported limestones on the shale shakers, which actually signifies we are going to the Buddha zone. At that point, we asked our geophysicists to step in, take a closer look and see if there's anything that we might have missed. There you go. It actually has a fault right there where we had issues with. Okay? And the greatest benefit that you have is as soon as you incorporate that fault, within this live updatable model, it automatically updates on the downstream side the offsets of our surfaces. You can see that from the top in the 3D view as well. It updates our surfaces so that it gives a clear picture where your lateral need to be headed in order to keep in the reservoir. So at that point, we asked our drillers to steer up their mud motors and get it back to the lower part of the Eagle Ford zone on the downstream side of the fault. Again, this information is like can be taken instantly into our drilling suite as well, because there's tools available not to send that trajectory information, the drill ahead or look ahead trajectory information directly into drilling suite that we have. Now that we have successfully steered the well, the next one is most important part basically. This is where most of our money for this particular well goes to, and this is the most productive part as well. So what you're looking at here is 3 different views, the cube view, map view, and at the bottom is the section view. Section view, this is a key thing where you can understand those micro fractures that exist within the system. Remember, those are the ones dictate the well positioning. And also you can bring in maps like the brittleness and understand what are my zones, how many stages I can have along the well, which are the brittle zones. You can do your zonal isolation here. And you can also visualize the same microseismic treatment in the 3D view as well. Let's actually take a closer look. For example, if you have the treatment going outside the zone, you can tell the guys, we need to just stop it because we are going out of the zone. It's not going to help out with any reservoir drainage. In fact, it will cause more harm if there's a water table right above that. So you get a clear picture where our microseismic events are in relation to your reservoir. And also if you're coming close to a fault, you can avoid that and not risk losing your entire well. So if you take a closer look, zoom in a little bit, you can actually see that yellow is our plan, and the red is basically our geostate. So if we had drilled it according to our plan, without frameworks, updatability, you would lose half of your well. You have to spend that extra money and effort in drilling a sidetrack. There are tools available within this stimulation module where you can calculate theoretically how much of your reservoir is stimulated. You can see it, how it actually updated the surfaces right across that well and gave us a better view. Now that's what we call the stimulated rock volume. Now you can take a look of the same data in the map view as well. So what you're looking at is those different stages. And again, this is what we started out with. We took the existing well frac information. Now we can combine this loop. We take the information, remember the frac direction is always in the natural fracs, right? The stimulation direction. Now the well is actually, the orientation of well is dictated by the natural fracs. Now we can take that information, average frac length, incorporate the fault as a subsurface hazard, and develop this entire fill. So what you're looking at here is we took all those stages, we made that as a uniform ellipses of stimulation, and we applied on the entire fill. Let's zoom out a little bit. You'll see that it actually applied for the entire fill and made that spacing, and it also had nice zipper frac between the adjacent treatments so that you're actually stimulating most of the rock. Now this is going to give you a more accurate picture of what would be my total reservoir drainage. So that would be the total drainage you can get, and of course the bottom line for this particular field. And that number will get updated on the fly. So in summary, what you have seen is basically we started out with the surface challenges we have in relation to our pad placement, for example. And next thing is we incorporated historical well information, and the geologists were able to grid up, correlate the top and base of our reservoir. Then we constructed a sealed structured framework, populated that with reservoir properties and phases to understand how much of my reservoir is actually occupied by hydrocarbons and where are those high TOC or total organic content. And we understand using those, we can efficiently lay out our laterals and efficiently drain the reservoir too. And then we ran into multiple exercises of field planning to come up with an optimum field plan that would work for this particular field specifically by learning the best practices from the wells that are drilled. And once we did that, we actually incorporated live data in order to understand how you want to geosteer this well as you're drilling. Okay, remember, as you're drilling. And not only that, we actually use the log signature you get from these wells and update our reservoir on the fly so that you know where you need to keep that lateral as you're correlating this. That is the dynamic updatability which nobody else out there even get close to that. And now once you're sure that you put your lateral in the right part of the rock, the next part is basically, of course, the most efficiently draining the reservoir, which is the stimulation. Since you actually model the reservoir more accurately, those microseismic treatments can be closely related to what is the right part of the rock I need to focus on. If you have a fault, how to skip it to next. So you can actually make those decisions on the fly. I use that information in relation to the azimuth spacing, and I combine this loop so that my model keeps updating as new wells come online. So this is what you need when you have 3 or 4 wells coming online. You want to learn from them and update the model on the fly. And this is the unique and perfect tool in order to make that happen. Thank you.